This conference will now be recorded.
Good afternoon, everyone.
Good afternoon, ma'am.
Good afternoon, ma'am.
Good afternoon, ma'am.
Good afternoon, ma'am.
Very good afternoon.
Good afternoon, ma'am.
This last class we had started with isomerism. Remember what is isomerism? The organic compounds having same molecular formula but differ from each other in physical or chemical properties are called isomers, and the phenomenon is termed as isomerism. There are two main types of isomerism, that is structural isomerism and stereoisomerism. We have discussed about structural isomerism, the definition, classification with examples. So today's class we discuss about stereoisomerism. So stereoisomerism is a type of isomerism when isomerism is caused by different arrangements of atoms or groups in space, then the phenomenon is called as stereoisomerism. So they have same structural formula but differ in arrangement of atoms in space. Only they are going to differ in arrangement of atom in space. So this is the chemistry of space, and it deals with the spatial arrangement of atoms or groups in a molecule. If you see the examples here, so what is the example I have given here? What is the first example? Can you name the first example?
1,2 dichloroethene.
Ethene, yes. And there are two structures here.
Yes, ma'am.
So what is the difference here in the structure?
Cis and
It has
trans.
same molecular formula, but you can see the arrangement of atoms in space is different. You can see in the first structure the hydrogen and you have chlorine on the above, one chlorine below and hydrogen, whereas in the second structure you can see both the chlorines above and both the hydrogens below. So first structure is it cis or trans? Which it is?
Trans.
Yes, when
Trans.
you have two different atoms, trans. If you have same atoms on the same side, then it is cis. So the first one is trans and the second one is cis. Similarly, one more example I have given. Can you name the second example? Yes, anyone can name? Can you try?
3 bromo,
Hmm.
1 chloro,
Hmm.
butane.
Why you are giving 3 to bromo?
Ma'am, because of the nomenclature name.
Hmm. Why you can't give 1 bromo, 3 chloro?
Ma'am, because the first letter
Hmm.
is I can't. I'm not able to explain, ma'am. Yes, ma'am. Alphabetical order.
B
Yes,
will come first or C will come first?
ma'am. B.
Then bromo should have 1, right?
Oh. 1 bromo, 3 chloro, cyclobutane.
Cyclobutane. So now here also you can see the difference. What is the difference here? Halogens. We have two halogen, one is chlorine and one is bromine. So first structure you have halogens on opposite sides, whereas in the second structure you have halogens on the same side. So the first structure is trans and the second structure is cis.
Cis.
So stereoisomerism refers to the isomerism that is caused by the non-similar arrangements of atoms or functional groups belonging to an atom in space. Especially we are talking the arrangement of atom in space. So these types of isomers have same constitutions but different geometric arrangements of atoms. So these molecules have one or more chiral centers. So this makes the molecules or compounds for possibility for forming the same chemical formula but differing in spatial arrangements. What do you mean by chiral? Have you heard about chiral or chirality?
Yes, ma'am.
So
The
what do you mean by chiral?
mirror image compounds.
That is called chiral.
Now, a carbon attached with the different groups
Yes.
like A, B, C, D.
So the carbon should be attached to 4 different atoms or group of atoms. Then you can tell it is chiral. When it is attached to same, like methane. Methane has carbon attached to 4 different hydrogens. All hydrogens are same. So there is no chirality. If you take other molecules, like example, can you give any one compound with chiral carbon? Butene, 2-butene. You can give an example for 2-butene. Is this chiral? Yes. Can you see the structure of butene?
Yes, ma'am.
Is it chiral?
Yes, ma'am.
How?
It is carbon is attached with the different groups: hydrogen,
Yes, it has one
methane,
hydrogen, one methyl, one double bond.
and double bond. Yes, ma'am.
So butene is an example for, but that is butene has a chiral carbon. So if you see the history, the Biot is a scientist who discovered optical activity, and Pasteur separated the enantiomers. Van Hoff, he gave tetrahedral carbon atom. Fischer identified the 16 aldohexoses. Prelog, he devised the terms RS and ZE. We'll come to later what is meant by RS and ZE. So what are the facts about stereochemistry? So if you see the facts, the structure of a molecule can vary based on 3-dimensional arrangement of the atoms that constitute it. And it also deals with the manipulation of the arrangement of these atoms. So you can manipulate, you can rotate. And this stereochemistry is a branch of chemistry which is commonly referred to as 3D chemistry because it focuses on stereoisomers. So they have same chemical formula but different spatial arrangement in 3 dimensions. When you see a 3-dimensional structure, will come to picture. It is stereochemistry. So stereoisomerism is mainly broadly classified into 2 types, that is geometrical isomerism and optical isomerism. Geometrical isomerism is also called as cis and trans isomerism or cis trans isomerism. So this arises or results from a restriction in rotation about the double bond or about the single bonds in cyclic compounds. So you can see stereoisomers is classified into geometric and optical. Geometric isomers is classified into cis and trans. Optical isomers are classified into enantiomers and diastereomers. So they have same molecular formula, represents 2 or more compounds. They are going to differ in spatial arrangement of atoms or groups around the carbon-carbon double bond. So it is of 2 types. If the same group are on same side, then it is called cis isomer, and if it is on opposite side, then it is called trans isomers. Example, here we have quoted cis 2-butene and trans 2-butene. So cis and trans are isomers. In cis 2-butene, the groups are on same side, like methyl groups are on same side and hydrogens are on same side. Whereas in trans 2-butene, the groups are on opposite sides. So now can you tell me propene? Does this have any isomer? So can propene has a geometrical isomer?
No, ma'am.
No. Why?
Because
One of
first
the
carbon,
double
first,
bonded carbon
yes, ma'am.
has two identical hydrogens. You can see
Hydrogen.
all
Yes, ma'am.
hydrogens are only present. No other groups are present. All are identical. So there is no geometrical isomers are possible for propene. 3-hexene. So for 3-hexene, can you have a geometrical isomer?
Yes, ma'am.
How?
Carbon is attached with the different first
Different
carbon groups. Yes,
That is
ma'am. First,
CH2, CH3.
CH2. Yes, ma'am. CH2,
And
CH3, and
one
hydrogen.
hydrogen. Yes. So you have two different. So there is possibility of geometrical isomers. So these are the possible isomers. You can see cis 3-hexene and trans 3-hexene. So cis you have the ethyl group on same side, whereas trans we have ethyl group on opposite side. So next butene dioic acid. So in this case, can we have an isomer? That is geometrical isomer.
Yes, ma'am.
Yes. Why? Because we have
Two
two
different groups.
different groups attached to the carbon, double bonded carbon. So what are the groups attached? One is hydrogen and the other is carboxylic acid, that is
Yes, yes.
COOH group. So what are the isomers of this butene dioic acid? Cis butene dioic acid and trans butene dioic acid. So we have a common name called cis butene dioic acid is called malic acid, whereas trans butene dioic acid is called fumaric acid. So these two isomers differ in physical properties like melting point, dipole moment, acidities, like this. They have a different physical properties. So the trans isomer has no dipole because it is symmetrical. Unlike the cis isomer, it is not identical. The cis isomer is stronger acid than the trans isomer. So even the chemical properties differ in butene dioic acid. Example, the cis acid undergo dehydration. So you can see here, the cis isomer is malic acid. So this malic acid undergo dehydration at 100 degrees Celsius to give you malic anhydride. But the trans acid also will give you anhydride, but it is not at low temperature. It requires high temperature, like 240 degrees Celsius. So first, the fumaric acid is converted into malic acid, then malic acid is converted into malic anhydride. So now when we see acyclic compounds, so geometrical isomers are possible in cyclic compounds as well. So this is an example of 1,2 dimethyl cyclopropane. So you have cis and trans form. So they are varying in physical properties like boiling point. The boiling point of cis 1,2 dimethyl cyclopropane is 37 degrees Celsius, whereas trans 1,2 dimethyl cyclopropane is 29 degrees Celsius. So that the geometrical isomerism is possible in cyclic compounds. So there can be no rotation about carbon-carbon single bonds forming a ring, because rotation would break the bond and break the ring. So in cis 1,2 dimethyl cyclopropane, the two methyl groups are on the same side of the ring, whereas in trans 1,2 dimethyl cyclopropane, they are on the opposite sides. So what is the requirement of geometrical isomerism in cyclic compounds is that there must be at least two other groups besides hydrogen on the ring, and these must be on different ring carbon atoms. They should not be on the same carbon, it should be on the different carbon atoms. So can you write a geometrical structure isomer for 1,1 dimethyl cyclopropane? Can you write a geometrical isomer for this?
No.
It's not possible because
Same hydrogen and methane on same side.
So this compound will have a geometrical isomer?
No, ma'am.
No, because
There are same groups present on the same side,
yes,
methane and hydrogen.
CH3 are present on the same ring carbon atom. If they would have present on different carbon atom, means there would be geometrical isomer. Since the methyl groups are present on same carbon atom, this 1,1 dimethyl cyclopropane will not have any geometrical isomer. So if you see an example of stereoisomerism, that is geometrical isomerism, it is found in some but not all the alkenes. So in some alkenes you can see geometrical isomerism. So how it occurs? It occurs due to the restricted rotation of carbon-carbon double bonds and get two forms. So you can see cis we have the same atoms on same side, and in trans the atoms or groups of atoms are on the opposite side. So these isomers have different physical properties like boiling point, melting point, acidity, dipole moment, density, etc. But they have similar chemical properties in most cases, not in all cases. In most of the cases we may see the same or similar chemical properties. So what is restricted rotation of carbon-carbon double bond? So here single covalent bonds can easily rotate. Yes or no? When you have a single bond, it is easy to rotate, but it is difficult for rotation in double bonds. So what appears to be a different structure in an alkane is not. So due to the way structures are written out, they are the same. You can see here. These are single bonds, that is covalent bonds having carbon-carbon single bond. So if you rotate, there is no breakage of bond. So all these structures are the same because carbon-carbon bonds have the rotation. But if you take carbon-carbon double bond, so there is restriction in the rotation. So restricted rotation, so the groups on either end of the bond are frozen in one position. So it is not easy to flip between the two. So it is not easier as compared to the saturated, that is carbon-carbon single bond compounds. So this produces two possibilities. The two structures cannot interchange easily. So the atoms in the two molecules occupy different positions in the space. So why this occurs, you came to know. Why the atoms will be arranged in different position in the space.
Yes, ma'am.
So due to the restricted rotation, we have the possible cis and trans isomers. So chair, it's a Greek word which means hat. So you have two hands. So two hands are identical. Are your hands are identical?
Yes, ma'am.
So what are the similarities between your hands? So it is a mirror image. Yes or no? It can be
Yes.
superimposable.
Non-superimposable.
Yes, it is not non-superimposable. Mirror images. So hand, if you take a mirror image, you will get the other hand. If you show your left hand, you feel mirror image of your right hand. So if you see molecules in the mirror, so that is mirror image. So asymmetrical carbon atoms will have the mirror image. Example we have taken here, cis-platin and trans-platin. If you shown in this mirror, the opposite what you get is the cis and trans isomers. So a compound containing an equal proportion of each enantiomer is called racemic mixture. So chiral switching means development of single enantiomers from old racemate drugs. We'll see this next slides. So according to rotation of polarized light, we have plus and minus, that is nothing but dextrorotatory and levorotatory compounds. And with respect to glyceraldehyde, we have D and L. And with respect to enantiomers, according to the Can, Ingold, Prelog priority rules, R and S enantiomers. So what is E and Z? They are also termed as cis and trans. Z stands for Zusammen and E stands for Enginen or Engigen. So Z, higher purity groups or atoms on the same side. So Z means cis or trans. Zusammen, Z. It means higher purity groups atoms on same side. Same side means cis. Cis is nothing but Z. Z means Zusammen. E is Enginen. So where we have atoms on opposite sides. So to determine priority, so that is we talked about higher priority groups. So according to the Can, Ingold and Prelog convention, we use this priority. So ethyl is more prior to methyl and methyl is more prior to hydrogen. And similarly, if you take halogens, iodine is the first preference, then bromine, then chlorine, then fluorine, then carbon, and last is the hydrogen. So cis or trans should only be used when there are two hydrogens and two non-hydrogen groups attached to each carbon. So you can see, so other than non-hydrogen groups on the same side, it is called cis. Non-hydrogen groups on opposite sides, it is called trans. So if you see the isomerism in butene, there are three structural isomers of C4H8 that are alkenes. Of these, only one exhibits geometrical isomerism, that is cis-butene and trans-butene. So these are the geometrical isomers. We can have but1ene and 2-methyl-propene also isomers, but they do not exhibit geometrical isomerism. So you can also get an alkane with formula C4H8 if the carbon atoms are in a ring, like cyclo or cyclic compounds. So the next is optical isomerism. So optical isomerism are named like this because of their effect on plane polarized light. So optical isomerism is a type of stereoisomerism. So the outstanding feature of optical isomer is that they have the ability to rotate plane polarized light. So this property is often referred to as optical activity. So optical isomers are non-superimposable mirror images of each other. They are called enantiomers. Example, if you take D-alanine, L-alanine and lactic acid, they are all optical isomers. So this is another form of stereoisomerism, occurs when compounds have non-superimposable mirror images. So the two different forms are known as optical isomers or enantiomers. They occur when molecules have a chiral center. A chiral center contains an asymmetric carbon atom. An asymmetric carbon has 4 different atoms or groups arranged tetrahedrally around it. So you can see in the first structure, there are 4 different colors arranged tetrahedrally about the carbon atom. So the 4 different colors indicates for 4 different atoms or groups. So the 2-chlorobutane exhibits optical isomerism because the second carbon atom has 4 different atoms or groups attached. So hence the 2-chlorobutane have optical activity. So how will you identify the chiral centers? So some examples I have discussed here. So look at each carbon atom in the chain and see what is attached to it. For a chiral center, you need an asymmetric carbon with 4 different atoms or groups arranged tetrahedrally around it. So if a carbon has more than one of any atom or group attached, it can't be chiral. So it should have 4 different atoms or groups. Then only you can say it's a chiral carbon. So first you see in chlorobutane, that is 1-chlorobutane. So 1-chlorobutane has how many carbons? 1-chlorobutane has how many carbons?
4.
4. So now check for chirality for each carbon in this. So go with, starting from CH3 you start, from left we'll start. So first carbon has chirality. Does the first carbon has chirality? Yes or no?
No,
No,
ma'am.
ma'am.
No. Why? Because the first carbon
2
has
hydrogen.
3 hydrogens around
3
it.
hydrogen.
So we have already said, if for a chiral center you need an asymmetric carbon with 4 different atoms. So now we already have 3 same hydrogens. So it is not chiral. Then go to second carbon, CH2. So here we have 2 hydrogens. So it's not chiral. Again go to third carbon. Again it has 2 hydrogens. Again you go to last. Again it has 2 hydrogens. So these are not chiral. So 1-chlorobutane does not have chiral carbon. So if it does not have chiral carbon, that means it is not optically active. So you will not have any optical isomers for 1-chlorobutane. So next you go to 2-chlorobutane. So in 2-chlorobutane, similarly, you start with the first carbon. The first carbon has 3 hydrogens around it and it's not chiral. The second carbon has 2 hydrogens around it. Again, it's not chiral. When you go to third carbon, you can see the chirality. So why it has chirality? The carbon is attached to 4
Chlorine.
different
Yes, ma'am.
atoms. One is hydrogen, one is methane, one is chlorine, and one is ethane. So 2-chlorobutane has chiral carbon. So chiral carbon means there is optical activity and there are optical isomers for this. And the last carbon, again it has 3 hydrogens, so it is not a chiral carbon. Similarly, for 1-chloro, 2-methyl propane, so it is propane, spelling mistake, and 2-chloro, 2-methyl propane, they don't have any chiral carbon. So what is the spatial differences between isomers? So two forms exist which are non-superimposable mirror images of each other. So what do you mean by non-superimposable? It means that you can't take one form exactly on top of the other. So when you take your hand, take left hand and top of that you keep your right hand. Can you exactly fix your right hand on left hand?
No, ma'am.
It's not possible. So that is non-superimposable mirror image. Some common objects are mirror images and superimposable. Some are superimposable but not mirror images. Some are non-superimposable but they are mirror images. So we have different variations. But for optical activity, it should be a non-superimposable mirror image. So for optical isomerism in molecules, both conditions must apply. That is, they must be a mirror image and be non-superimposable. Then only you can see optical activity and optical isomerism. So what is the difference in optical isomers? So isomers differ in their reaction to plane polarized light. So when they are passed through plane polarized light, so they are going to differ in activity. They are either going to rotate the plane polarized light towards left or towards the right. And plane polarized light vibrates in one direction only. One isomer rotates light to the right and the other to the left. The rotation of light is measured using a polarimeter. So we need a device called instrument called polarimeter. By using this, you can observe the optical activity. So rotation is measured by observing the polarized light coming out towards the observer. So if the light appears to have turned to the right, then it is dextrorotatory, or you can use small d or plus form. If the light appears to have turned to the left side, then it is called levorotatory, and it can be symbolized with small l or minus form. So what do you mean by racemate? Racemate means it's a 50-50 mixture of the two enantiomers, that is both D and L or plus or minus. So if you have equal mixture of both dextrorotatory and levorotatory compounds, it is termed as racemic mixture. The opposite optical effects of each isomer cancel each other out. Hence, the racemic actor will not have the optical activity because one will cancel with the other. So, more optical activity is common in biochemistry and pharmaceuticals. We use this optical isomerism. So, most of the amino acids exhibit optical activity. Many drugs must be made of one optical isomer to be effective. If you take some of the isomers, like example D-glucose and L-glucose. The D-glucose is most commonly used. So it has some more effect compared to L-isomer. And some drugs will have some side effects, and one of the isomer will have good therapeutic effect and the other isomer will have the most side effect. So this optical activity plays an important role in choosing the drugs. So many drugs must be made of one optical isomer to be effective and need smaller doses, safer and cost effective. So and they get reduced side effects. They are going to improve pharmacological activity when you separate a specific isomer and use it. So we'll see what is optical activity. So this is the what you call arrangement of how you can observe polarized light, optical activity, how you can observe optical activity. So you have how many? 1, 2, 3, 4, 5. That is A to F. So what is from A? We'll see. A is a light source, produces light vibrating in all directions. So that is the ordinary light. So what you have, the ordinary light will have the directions in, will have the vibrations in all directions. They are not in one direction. They are scattered. So next we have B. B is the actually a prism. We are going to use a prism. So it is a polarizing filter which only allows through light vibrating in one direction. So you can see in this picture there are various direction of the light. So when it passes to the Nicol prism, so whatever the extra other directed light is removed, only in one direction it is coming out from the prism. The C is the sample. So where you can keep your sample in the what you call sample holder. So you can place your sample solution. C is a sample solution. So through this, a plane polarized light is going to pass through your sample. So after passing the plane polarized light through the sample, so next D. So if the substance is optically active, what happens? It rotates the plane polarized light either to left or either to right. So either clockwise or anti-clockwise also you can say. So after that we have an analyzing filter. So this analyzing filter is turned so that light reaches the maximum. You can clearly see the light or which side it is bent. And the final F is the direction of rotation which is measured coming towards the observer. You can see through your eyes. So which direction the light is coming out. So if the light appears to have turned to the right, then you call it as dextrorotatory. And if the light appears to have turned to the left, then we call it as levorotatory. So you can see when you have two different optical isomers, so the light source, from light source you'll get the ordinary light source, you'll get the light in all directions. So light beam showing random orientation of electromagnetic waves, which is in all directions. Then after passing through the filter, there is a plane polarization. It is going to oscillate in one direction. After passing through the sample, you can see the direction of polarized light either towards left or towards the right. So if it is directed towards the right, it is called dextrorotatory. It is directed towards the left, it is levorotatory. So enantiomeric molecules have the same relationship as right and left hand. So enantiomers and hands are chiral. So they possess the property of chirality. Molecules or other objects that are not chiral are said to be achiral, that is without chirality. So receptor sites for the sense of smell are chiral, just as the active sites in most enzymes are chiral. So our nose can distinguish between the enantiomers. So this is an example of enantiomer, that is carbon plus and carbon minus, that is dextrorotatory and levorotatory. So you can distinguish this enantiomer with the smell. So they have different odors. So the drug example is ibuprofen. So ibuprofen we have S isomer and R isomer. Similarly, we have thalidomide. So plus thalidomide and minus thalidomide. So it has different activity. You can see thalidomide plus can be used for anti-nausea and minus thalidomide teratogen. So have you heard what do you mean by teratogen? Teratogen. So these are the agents that are going to inhibit or disrupt the development of embryo or fetus. So thalidomide should not be given to a pregnant lady. So it may lead to birth defect in the child. So how can we tell if a molecule is chiral? So two things you need to see to check for the chirality. So the one is look for a plane of symmetry. Second, look for a tetrahedral atom with 4 different substituents. So if you see this, you'll come to know whether the compound is having chiral or not. So a plane of symmetry divides an object or molecule into 2 equal halves that are mirror images of each other. So an object that has a plane of symmetry is superimposable on its mirror image and it is achiral. A chiral molecule does not have a plane of symmetry. So chiral molecules means it should not have plane of symmetry. If the molecule has plane of symmetry means they are not chiral. They are achiral. Then look for a tetrahedral atom with 4 different substituents. So a tetrahedral atom that is bonded to 4 different substituents constitutes a stereo center. It is called chiral center or stereogenic center. So if there is one chiral center only. So can you see here 2-butanol. So 2-butanol has 4 different atoms. So to change from one enantiomer of 2-butanol to other enantiomer, you have to physically remove 2 bonds and switch them. And 2-butanol is a chiral molecule which has a chiral carbon. What are the properties of enantiomers? Enantiomers have identical boiling point, melting point, solubilities, refractive index, IR, NMR in achiral solvent, etc. What do you mean by IR, NMR? They are the what you call it? Qualitative analysis of the compound, that is infrared radiation analysis and nuclear magnetic resonance effects. They have the same. So enantiomers differ when they interact with other chiral substances. And they differ when they interact. Yes?
Ma'am, can you repeat IR and NMR?
IR is infrared radiation. We'll be
okay.
analyzing the substance for their presence. It is a qualitative analysis. So they have same reading. When you take an IR analysis of the sample, so you get same reading for both the enantiomers. NMR is nuclear magnetic resonance. That is also, we'll get a graph for the compound that will be same. Enantiomer will have the same. You can't differentiate. Either it is a dextrorotatory or levorotatory compound. So we can't make it out by this IR and NMR study.
Okay.
So enantiomers rotate the plane of polarized light by exactly the same amount, but in the opposite direction. So whatever the dextro and whatever the levo, so the polarized light, when you are getting it is either towards the left or right, will have the same amount, same intensity. So the device used to measure optical rotation is termed as polarimeter. So a sample of pure chiral compound uncontaminated by its enantiomer is said to be enantiomerically. An equimolar pair of enantiomers is termed as racemic mixture. A racemic mixture has an optical rotation of 0. So chirality is a property of individual molecules or objects. A chiral molecule has this property whether it's mixed with its enantiomer or not. Optical activity is a physical property. Chirality is a structural property. So don't confuse configuration with conformation. What do you mean by configuration? Configuration is fixed for the compound. It is not going to change. Configuration of a compound is unchanged unless at least one bond at the stereo center is broken. Unless the bond is broken, the configuration will not change. Whereas conformation means a molecule changes continuously at room temperature as a result of rotation about single bond and the flipping of rings in molecules. So a stereoisomer has a single configuration but may exist in a number of conformations depending on solvent and temperature. So these are having a single configuration but you can represent in 3 conformations. So absolute configuration is specified by using R and S, that is scan, encode, pre-log rules. Here R stands for rectal or right-handed, where the light is rotated towards the clockwise. The plane polarized light is rotated towards the clockwise direction, and S stands for sinister or left-handed. It is the counter-clockwise or anti-clockwise. So when the light is reflected towards anti-clockwise direction, it is called S. So similarly, we have different stereoisomers like atroph isomerism, cis-trans isomerism, conformational isomerism, stereomer, and enantiomer. So if you see what is atroph isomerism, it is the property of any molecule or object of being non-superimposable on its mirror image. Cis-trans shares the same atoms which are joined to one another in the same way but have a different configuration. Conformational is a type of stereoisomerism in which isomers can only be converted by formally single bond rotations. Diastereomers are optically active isomers that are not enantiomers. So diastereomers do not behave as a mirror image of each other. They are diastereomers. So a molecule with n number of symmetric carbon atoms can have up to 2n diastereomers. When two diastereomers differ at only one stereocenter, they are referred to as epimers, and these isomers vary in physical and chemical properties. Enantiomer is one of a pair of optical isomers, the structures of which are not superimposable on their mirror images. So they are stable and isolable compounds that differ in their spatial arrangements in 3D space. They generally exist as discrete pairs. So the properties of enantiomers are identical. However, the interaction with plane of polarized light can vary only in rotating the plane polarized light. The direction in which they rotate the plane polarized light is different. That is, if one rotates in the right direction, the other is going to rotate towards the left direction. So you can see enantiomer example. Yes.
Ma'am.
Yes.
Ma'am, what is the difference in optimoisomerism and this is enantiomerism? Aptioisomerism. Yes.
So apti is telling about, sorry, atrophy. Atrophy is
Atropioisomer.
Yes, so just it is non-superimposable mirror image. That's it. But this enantiomer will have this polarized, plane polarized light. They are going to rotate towards left or right. So I will share this slide after the class. You can go through this. If you have any doubts, you can come back.